Greetings to everyone. We, the Team Fusion Sprint crew, and our project for Smart India Hackathon 2025 focuses on redesigning a prosthetic J shaped leg. This comes under the problem statement ID SIH 25095. This problem statement focuses on redesigning a commonly used sports equipment. The prosthetic J shaped leg, which is used by athletes, especially in running and jumping events. The idea is to use Fusion software tools to reimage its design. Generative design and topology optimization, which is the tools to create a stronger yet lightweight structure. Additive manufacturing enables affordability, easy customization for each user, and fast prototyping. Expected outcome: a redesigned prosthetic leg that is more innovative, efficient, and comfortable while optimized for 3D printing. This falls under the smart education in hardware category as it promotes the use of advanced design software and manufacturing methods of real-world applications. Now we are moving to our proposed solution. We are using generative design and topology optimization to achieve a strong yet lightweight structure. Additive manufacturing, which ensures affordability and customization for individual users. The ergonomic designs mimics the natural human motion and unique curved J shape improves energy return, gives athletes more efficiency during running and jumping. In short, our solution combines advanced technology with user-centered design to create a high-performance prosthetic leg that is both functional and accessible.
Hello everyone. Now I will explain the technical approach that we plan to follow for developing our prosthetic J-shaped leg. Our goal is to design a lightweight, high-performance prosthetic leg that closely mimics natural movement and improves energy return during sports activities. To achieve this, we are planning to combine advanced design tools like Autodesk Fusion 360 with additive manufacturing, mainly 3D printing for a faster, cost-effective, and customizable production. The first step in our technical approach will be research and requirement analysis. At this stage, we gathering detailed information from various research papers, journals, and case studies related to the prosthetics, biomechanics, and sports science. By studying these resources, we can understand how current prosthetic legs are designed, what their strengths and limitations are, and how athletes are actually use them in real scenarios. Then CAD modeling in Fusion 360. Once we have a clear understanding of the requirements, we will create a detailed 3D CAD model for our proposed prosthetic leg using Fusion 360. This stage will allow us to explore different shapes and forms digitally and visualize how the leg would behave in a real world use even before the physical prototyping. Then generative design. After that, we will use generative design to automatically generate multiple optimized design options based on the inputs we provided, such as load conditions, materials, and strength targets. We also plan to include a lattice structure integration to improve the strength to weight ratio and virtual validation to ensure the performance. This will help us to optimize the design for improving both performance and efficiency. Topology optimization. Once we selected the best concept, we will refine it further using topology optimization. This process removes unnecessary material while keeping the structure strong. This result will be a prosthetic that's a lightweight but highly durable, which is essential for athletes who need maximum agility and speed. Simulation and testing. Before moving to physical prototyping, we plan to run a virtual simulations in Fusion 360 to test how the prosthetic performs under different stress conditions. This helps us to check things like load bearing capacity, energy return, and structural safety. Any design issues can be identified and fixed early at this stage. 3D printing under prototyping. With a validated digital design, we will move to additive manufacturing. 3D printing will allow us to build prototypes quickly and with a high precision and at this lower cost. It also makes customization easier. Finally, we will conduct a final evaluation by testing a physical prototype and assessing its overall performance. Then this stage will help us to confirm if the design meets all functional, ergonomic, and safety standards we are aiming for. Now, let's discuss the feasibility and viability of our proposed solution, along with some potential challenges and how we plan to overcome them. First, our approach is highly feasible because it relies on additive manufacturing, which is significantly reduces the production cost and the material waste. This makes the prosthetic more affordable and scalable compared to traditional manufacturing. However, we are aware that every solution comes with challenges. One of the main challenges is ensuring the structural strength of the prosthetic while keeping it lightweight. To tackle this, we plan to use topology optimization and lattice structure, as we already discussed, which allows us to remove unnecessary material without compromising the durability. Finally, the material selection could be a limiting factor when trying to achieve both the high performance and low cost. To address this, we plan to explore uh, and test advanced 3D printing materials that deliver the optimal balance of flexibility, strength, and affordability. Our goal is to choose the material that enhance the overall performance without increasing the production cost, ensuring the final prosthetic is both effective and accessible. With that, I conclude my part on the technical approach and feasibility and viability of our proposed solution. The upcoming topics will be explained in detail about my one of my teammate. Thank you.
For our solution, we create impact at three levels. First, athletic performance. The optimized play geometry improves energy return and endurance while reducing shock load to minimize injuries. The stiffness to weight ratio ensures better speed and efficiency. Second, economic. Unlike elite prosthetic weights that are extremely costly, our design provides a low cost alternative that can be widely used for training and competitive sports. Third, social and environmental impact. We make sports more inclusive, giving differently abled individuals greater accessibility. At the same time, using generative and additive manufacturing helps us cut down materials waste and makes the solution eco-friendly. So overall, our project is not just about the engineering, it's about affordable, inclusive, and sustainable sports innovation. This slide shows the research-based beginner idea. We have reviewed sports science journals, especially biomechanics of prosthetic. We also studied additive manufacturing in sports, which guide our choice of materials and processes. Additionally, we refer to research paper and case studies on prosthetic blade design and innovation in manufacturing techniques. These references validate that our solution is scientifically grounded